So we've seen how we can develop very simple change detection algorithms using, say, for instance, the average or the median. And we can even make these adaptive, but we've also seen that there are limits to these kind of approaches. It's very difficult for such approaches to be able to be resilient to uninteresting changes. In order to do that, we need a more sophisticated model for the variation of intensities or colors at each pixel in the image. So that brings us to the Gaussian mixture model. So here is our very challenging scenario, which is we're looking at a street scene. We have cars going by. Let's say we wanted to count the cars that are actually passing by or figure out which cars are violating traffic rules. But what we have is this window which has lots of raindrops on it, and raindrops could be moving around. And of course, we have snow, bad weather. So all of this adds to the complexity of the scene. Now let's consider one pixel here, shown by this red window right here. And let's watch this pixel for a certain amount of time, let's say 1,000 frames. We take the intensity values, and we'll talk about intensity for now and then color later. But let's just look at the brightness values, and we essentially compute a histogram of the brightness values. So that's the histogram that you see right here. The values go from 0 to 255. Let's say it's an 8-bit image, and this is the histogram corresponding to that pixel. So we want to understand the structure of this histogram. Fairly sophisticated and detailed in terms of variations. There's a lot going on in here. Well, the first thing to notice is that the fluctuations or the variations in intensity are essentially due to three things. The static background or the road, which may or may not vary with time, but it could vary because of, say, for instance, illumination changes. Noise, in this case, could be image noise, but also the fluctuations due to snow passing through the pixel. And then occasionally you have a moving object, which the key observation here is that the moving object is something that passes through a pixel rarely. Most of the time you have the other two things going on. And so what we really have here when we look at our distribution is that you have these peaks here. So you can view this statistically, you can view this as a population of intensities. And you can see each one of these bumps as being a subpopulation, if you will. So this one right here corresponds to the intensity variations due to the road itself. And this one is due to the snow, which are these bright values that are passing through the pixels. And then you have the occasional car that passes through, and that's what produces this distribution right here. So intensity variations due to the static scene and noise, which are colored in blue, and then you have the occasional moving object or vehicle, which is shown in red right here. So the intuition here is that pixels are background most of the time. It has to be, because if a car comes in and sits on a pixel and it stays there, then at some point you have to declare that car as being a part of the background because it's now become a part of the static scene. All right, so with that intuition in place, we're going to try and model this distribution and then classify pixels as belonging to the background or the foreground. So for that, we're going to use this Gaussian model. So let's just take a look at a single Gaussian. Let's say that this is our distribution right here, and we're looking at this mode here, this mode right here, and this bump, and we want to model this using a Gaussian. Well, if we fit a Gaussian to just that data, you might get something that looks like this. That's your Gaussian. And this Gaussian, as we know, has a width, which is given by sigma, and it has a mean, which is given by mu. So that's your normalized Gaussian right here. And we're going to add a third parameter to it, which is omega. Omega is called the scale or the evidence associated with this Gaussian. And that's to accommodate for the fact that these various subpopulations or bumps can be of varying heights. So that's your Gaussian. So we can certainly model one of these peaks or modes with one Gaussian. And that's a one-dimensional Gaussian in this case because we're looking at just brightness values. So that same logic can be used to say that now if you view our entire intensity variation histogram as a collection of Gaussians, and if somehow we were able to figure out what the parameters of these Gaussians are, we should be able to get a fairly good representation of the histogram using a mixture of Gaussians. So we have 3 Gaussians here. You mix them up, which means you simply add them up and you end up getting this, which is very close to the actual histogram shape itself. So that's the idea. We are going to fit a Gaussian mixture model to the histogram. And so in other words, we have the model, which is a weighted sum of k Gaussians. And so that's what's shown right here. Each Gaussian has its own mean, its own width, which is sigma, and also its own evidence, omega. And the sum of the omega should be equal to 1, so that finally what the model gives you is also a distribution. It's normalized. Okay, now this can be taken to higher dimensions quite easily. Let's say that we had not just brightness or intensity, we actually wanted to represent these variations, pixel variations, in color space. So that would be R, G, and B right here. So you can do this modeling using Gaussian mixture models for any dimension of data, d-dimensional data, but in our case, d is equal to 3 as an example right here because we have red, green, and blue. So in this case, what we need to do is to see the distribution as a sum of high-dimensional Gaussians, k-dimensional. There are k d-dimensional Gaussians. D in our case, once again, is 3 in our example. So you have a sum of Gaussians here. It's exactly the same equation we saw before. And now we still want the sum of our evidences, which is our omega k's, equal to 1. But in this case, each Gaussian has a mean, which is actually a mean vector. So you have a mean for red, mean for green, and a mean for blue. And instead of sigma being a single number, that's your variance, a standard deviation, sigma, you now have a covariance matrix, large sigma right here. This is your covariance matrix. So imagine your Gaussian in high dimensional space. Let's start with 3-dimensional space. In this case, you may have the same sigma along red, green, and blue. That means it's a symmetric Gaussian. In that case, your covariance matrix would have sigma squared down the diagonal, the same value, and 0 everywhere else. And if you have different sigmas along red, green, and blue, you would still have a diagonal matrix, but these sigmas would be different. Or you could have a Gaussian that is rotated, which means that there is actually correlation between different dimensions, red, green, and blue. So it's kind of a rotated Gaussian, in which case this can be a full matrix. You would have non-zero values here as well. So it could be simple or more complex, doesn't really matter. So that is your GMM model, Gaussian mixture model in high dimensions. And we can actually take any distribution, irrespective of its dimensionality, and use existing algorithms. In MATLAB, you have this function called gmdistribution.fit. You can fit a mixture of Gaussian model to that distribution. And you have to decide what k is, how many Gaussians you want to use to do this fit. If k is very large, you can imagine that the data can get very unstable. If k is too small, your fit is going to be inaccurate because you don't have enough flexibility in the model. All right, so let's come back to our problem now. How do we use the GMM model? So given a Gaussian mixture model for intensity or color variation at a pixel over time, we're going to have the following problem to solve, which is we want to classify each one of the Gaussians as being either foreground or background. So first we want to figure out, we have a model now, we want to figure out which Gaussian represents the foreground and which Gaussian represents the background, so that when we see pixel values in the future, we can classify them according to that kind of a classification of the different components. So here you have your 3 Gaussians associated with this particular distribution. And once again, our intuition is that pixels are background most of the time. That is, the Gaussian with large supporting evidence and small sigma, which would be this and this one right here, are really going to be background Gaussians. So if you have omega divided, omega being the evidence, divided by sigma, the standard deviation, is large, then we're going to call that a background Gaussian. And then wherever you have omega divided by sigma small, we'll call that a foreground Gaussian. This is the one that ultimately we want to detect as a meaningful change when we see a new pixel value. So with that, we can develop our algorithm. This is actually an algorithm proposed by Stauffer, and I'm showing you a simplified version of that algorithm. So this is what we do. For each pixel, I'm going to do the same thing for all pixels. For each pixel, we compute, let's say we are functioning in color space, RGB, we compute a pixel color histogram H using, say, the first n frames of the video. And then we're going to normalize this histogram. We need to normalize to make sure that it's actually a distribution. So that's H hat. So now we're going to fit a GMM to H hat. And let's say for our purposes here, we pick K is equal to 3, 4, or 5. We'll just a small enough number. Beyond 5, that's getting really complex as a model. So we fit a GMM to H, and now we're ready to classify pixels. So what do? For each subsequent frame, we take the pixel value, X, at a given pixel, for the same pixel here, pixel value X, and we find which Gaussian in our model it is closest to in terms of proximity. That is, which mean value, mu k, is closest to X. And we'll say, well, that is the Gaussian that this pixel value belongs to, provided it's close enough to it. That is, not only are you finding the closest Gaussian, but it also should be close to that closest Gaussian. And that's what the second term here, X minus mu k, should be less than 2.5 sigma k. You want to be within that distribution of within that Gaussian. Okay, so that's what we do there. And then we go and take a look at what that type of Gaussian, what the Gaussian is that it belongs to. We know which Gaussian this pixel belongs to, but we want to know what type of Gaussian that is. That is, we look at its omega divided by sigma. If that's large, then we know that that's a background Gaussian, so the pixel is a background pixel. Otherwise, it's a foreground pixel. It's that simple. And now there's one little thing to worry about, which is updating the histogram. So we don't want to do this for every frame. That is, we'd be recomputing Gaussian mixture models at perhaps millions of pixels for each frame. That would be just onerous, computationally too intensive. So what we do is we simply update the histogram for that pixel, H. And then we find H divided by the magnitude of H, so that's your normalized histogram right here. If the normalized histogram differs from the current histogram that we have substantially, if that difference is large, then we would replace the histogram with the new histogram and refit a Gaussian mixture model. So this happens rarely. You can imagine that a single pixel value is not going to change a histogram substantially, but over time you might find the deviation to be large, and then you recompute the histogram, replace it, and then also refit a Gaussian mixture model. And you keep going. So let's take a look at how well this works. So here are these examples we were looking at. This is the one with people walking around. And you get a fairly nice result here. The only thing that's still problematic here is that you do have these shadows attached to the people walking around. There's no obvious way to take care of that. It's actually doing better in terms of shadows, but not perfectly. Here's your traffic example, and in this case you can see that now your algorithm is fairly resilient to all the waving, the swaying of the leaves in the background right here. and it's able to detect the vehicles fairly well, distinct from each other, not leaving around any traces. So you can imagine that each one of these can be seen as a potential region of interest, which we can use for further processing, as we will see shortly. Okay, now let's take a look at a more challenging example, which we looked at earlier, which is our bad weather scene. This is the result that you get using the moving median method, which is the best of the simpler methods that we talked about. Not very useful result. But here you see that you do pretty well with the adaptive GMM method. You see that the moving cars actually pop out pretty well, and the result is fairly insensitive to the rain and the snow and even the droplets on the window itself that are moving around.